Welcome. The topic we'll be discussing in this lecture is uncertainty. So we'll be discussing a brief introduction to how an agent should behave in an uncertain environment, in which we see that an agent should, in which we see what an agent should do when not all is crystal clear. There is the agent is unable to make a precise decision, then in such situation, what it is supposed to do. That is what we are going to discuss. Okay. Right. So what is so the whole topic is about acting under uncertainty. If things are clear, then that's fine. But if the things are not clear, then how the agent should behave. So when an agent knows enough facts about its environment, the logical approach enables it to derive the plans. That is, if the agent knows enough info about the environment, then you can go with the logical approach. Because logical approach basically deals it tells precisely, if this is the thing, do this. If this is the thing, do this, like that. But in case of uncertain environment, we cannot depend on logic, right? But in most of the real world cases, the real world environment uh, is not precise. It's not precise. That is you cannot say that exactly it is like this, so you can arrive at this type of conclusion. No. So most of the real world environments are uncertain. So agents must therefore learn to act under uncertainty. Okay. So agents should therefore learn to act under uncertainty. Let us consider one example. Assume that there is an intelligent agent that wants to drive someone to the airport to catch the flight. Okay, and the agent uses a plan, and that plan is called as A90. So the plan A90, what it says in the sense, it the plan A90 involves leaving home 90 minutes before the flight starts and driving at a reasonable speed. Okay, and we assume that the airport is somewhere around 10 to 15 kilometers from the agent's home. It is less than 15 kilometers uh, from the starting point. Okay, so with this assumption, the agent will this is the plan which is proposed by agent, which says that we have to start before 90 minutes, and the driving will be done at a reasonable speed, and then so this is the plan proposed by the agent to reach the airport by flight. Okay, see, now even though the airport is only 50 miles away, the in this case the agent will not be able to conclude with certainty that the plan A90 will get us to the airport in time. So what is the reason? The reason is, of course, most of the time the plan A90 will be successful. Most of the time the plan A90 will be successful. That is, it will be able to take the particular person to the airport on time. But it cannot always arrive at that conclusion. So hence it will arrive at a weaker conclusion, which says that plan A90 will get us to the airport in time as long as it put many conditions. As long as my car doesn't break down, or run out of gas, or I don't get into an accident, or there are no accidents on the bridge, and the plane doesn't leave, and the plane, that is the flight, doesn't leave early, and so on and so forth. So basically it cannot precisely say that this plan will take the individual to the airport on time, right? So it will arrive at this type of conclusion, which says that the plan A90 will take the individual to the airport on time as long as all these things were not happens. Okay, but none of this can be deduced. We cannot infer anything in advance, so the plan's success cannot be inferred. So this type of problems is called as qualification problem. This type of problem is called as a qualification problem, and most of the real world problem are like this. Okay, so here always there is some uncertainty is involved. So in such cases, how the agent should react, that's what we are going to discuss. Fine. So pure logical agent will not be able to conclude. In this case, if you use logical agent, it cannot be it won't be able to conclude that A90 is the right thing to do. Right? Now suppose A90 is the right thing to do, then what does this mean? So if you say that A90, but in spite of all this uncertainty, if we say that A90 is the right thing to do, then what does it mean? So it means that if we say that A90 is the right thing to do, it means that A90 is expected to maximize the performance measure. If this is the plan which maximizes the performance measure, then we can say that this plan is the right plan. So what is performance measure? So performance measure may depend on several parameters. For this example, the performance measures involve getting to the airport in time, avoiding long and unproductive wait at the airport. This is the two performance measures here. Okay, this is the two main performance measure here. It is getting to the airport on time, avoiding long and unproductive wait at the airport. There may be another plan A120. There may be another plan A120 which might increase the agent's belief that it will get to the airport on time, but also increase the likelihood of long wait. Okay, but so there may be another plan A120. This might improve the performance measure of getting onto the airport on time. It may take the individual to the airport on time, but also it increases the likelihood of long wait. So it all depends on like for which parameter you give more weightage and which one you give less weightage. Accordingly, the right action or the right plan will be deduced. Okay. So the right thing to do, that is what the rational decision is. So the right thing to do, that is the rational decision, depends on the relative importance of various goals and the likelihood that and the degree to which they will be achieved. So the rational, there is no, you cannot say that this is the rational plan. So the rational plan, actually it depends on these things. It depends on the relative importance of various goals. How much importance you are giving. So the entire goal itself can be split into several small goals, like or you can say it is performance measure, or G1, G2, G3, so far. G1, G2, G3, like that it goes on. There can be many goals. So the rational decision actually depends on the relative importance of various goals. How much importance you are giving for G1, how much importance you are giving for G2, how much weightage. So importance means we can call it as weightage. How much weightage you are giving for G3 and the degree to which they will be achieved. So based on that the rational decision may change. Okay. So it all depends on the user's requirement. Fine. So this is a brief introduction to dealing with uncertainty. Now let us discuss some more example. Let us consider the example of performing dental diagnosis or representing dental diagnosis using FOL, first order logic. Say that we are representing something like this. For all P, symptom of P, toothache implies disease of P, cavity, which means that for all persons, if the person P, if the person P is having a symptom and that symptom is toothache, which implies that the person P is having a disease and that disease is cavity. Now this is actually a wrong rule. This rule is not correct, because this rule says that whenever a person is having toothache, he is having a cavity, but that need not be the case. Someone may have toothache for some other reason. They may have some gum problem or some other issues. So it's not that always a person with toothache should have cavity. Okay. So now then how do we change this rule? Then this rule can be changed something like this. For all P, symptom of P, toothache, that is if the person P is having toothache, then it implies that the person P is having cavity, or the person P is having the disease gum disease, or the person P is having the disease abscess, or so on and so forth. The list goes on. Now in the second case of representation, the problem is you have an unlimited list of possible causes for the for for toothache. So this list is a very big list. Again, representing this huge list is quite impractical, right? So here is another rule which is of this form. For all p, disease of p comma cavity implies symptom of p comma toothache. It says that. So this type of rule is called as causal rule. Okay, cause, it's a cause and effect. It's CAUASAL. Okay, so for all p disease of p comma cavity, if the person p is having the disease cavity, then it implies that the person p is having toothache. So this says that whenever there is a cavity, if someone is having a cavity, then they have a toothache. Again, this is also not right, because not all cavities cause pain. Somebody may have cavity and still they may not have toothache, right? So what we are discussing here is a challenging the challenges we are facing in representing the real world scenarios using first order logic, right? So FOL, to cope up with the domain like medical diagnosis, basically they fail. So we are unable to represent things in medical diagnosis using the tools like FOL. So basically FOL fails because of three reasons. These three reasons are called as laziness, theoretical ignorance, and practical ignorance. What is laziness? So the laziness here, it means that there are too much list of there are too much work, there are too much details to list out in the either in the antecedents or in the consequence or in both. So normally it is not possible to list everything. So this phenomenon is called as laziness. For example, here if you take, for all p, symptom of p comma toothache implies the either the person can have cavity, or the person may have gum disease, or the person may have abscess, so on and so forth. The list is very long. Actually, it is not possible to list out everything. So this is actually an example of laziness. So this is one of the reasons why FOL fails in representing medical diagnosis details. And the second reason is theoretical ignorance. Theoretical ignorance, what it says, means the medical science has no complete theory of the domain. Even the field of medical science, even they don't have the complete theory of the domain. That is, for example, somebody is having a toothache means there can be plenty of reasons. Even there can be some reasons which the medical experts are not aware of, right? So this is also one of the reasons why we can't represent these things with FOL. The third reason is practical ignorance. Practical ignorance, what it says is, even if we know all the rules, not all rules can be run out on a patient. Say for example, here you are saying that somebody is having toothache, it implies that either they can have cavity, or they can have gum disease, or they can have abscess. Like that, say there are some 100 possibilities were represented. Now if somebody come with a toothache to the doctor cannot check all these 100 things, right? It is not that the doctor is going to check all these 100 things and he is going to suggest, finally tell what is his problem. So we are not going to do that, right? So that's what this says. Even if you know all the rules, you cannot run all the rules on a patient. So these are the three main reasons. So practically we don't do that, right? So the doctor, with his experience, he will try to figure out what is the problem. So these are the main reasons why FOL fails in case of medical fields like medical diagnosis: laziness, theoretical ignorance, and practical ignorance. And there is no logical connection between toothache and cavities, right? So the agent's knowledge can be best provide only a degree of belief. So here, now if you are trying to solve the problems of medical diagnosis using an intelligent agent, the intelligent agent cannot arrive at a precise decision. The agent has to make decision only based on degree of belief. Okay. So the right tool to deal with degree of belief is probability theory. So whenever we want to perform something using degree of belief, then we have to take the help of probability theory, because that is the tool. Our main tool for dealing with the degree of belief is probability theory. Okay, hence we'll be discussing a brief intro to probability theory. So before that, consider this example. Let us assume that 80% there is an 80% chance, that is a probability of 0.8, that the patient has a cavity if he or she has a toothache. So based on the history of the medical diagnosis data, you know that 80% of the cases, if a person is having cavity, then he will be having toothache. Then when somebody is having a toothache, so for 80% cases you can confirm that it is a if 80% of the person, whenever somebody is having a cavity, for 80% of the time you can conclude that they are also having toothache. The missing 20%, it basically summarizes all the other possible causes of toothache. There may be you may be having a huge list. So those huge list will from those huge list, there may be any one of the reason for the remaining 20% cases. Okay, that were too lazy or ignorant to confirm or deny. So because the list is very huge, so that actually comes under the issue of laziness. Now we cannot check all the conditions and we can find why a person is suffering with a cavity, right? Because the list is huge. So this comes under the issue of laziness. Okay. For something, if you assign a probability of 0, then it means that unequivocal belief that the sentence is false. Then we are saying that the sentence is false. For something, if we assign the probability as 1, then we are saying that the sentence is true. Okay. So, but the probabilities between 0 and 1 corresponds to intermediate degree of belief in the truth of the sentence. So, if you apply something between 0 and 1, then that is the intermediate degree of belief, right? So there are two things here. One is degree of belief and degree of truth. Actually, these two things are different. So we are talking about degree of belief. So degree of belief is about probability theory, right? Whereas degree of truth is a subject of fuzzy logic, which later we will be discussing briefly. Okay? So here our focus is on degree of belief, that is probability theory. Okay. So there are two types of probabilities which we will be discussing. One is called as prior or unconditional probability, and the other one is called as posterior or conditional probability. That is before any evidence, before any evidence. If we don't have any evidence, then we talk about prior or unconditional probability. If we have some evidence, then we will be talking about posterior or conditional probability. Okay. Later we will be discussing some examples for this, right? Okay. So the presence of uncertainty radically changes the way in which agent make decision. So when uncertainty comes into the picture, it basically changes the way in which the agent makes the decision, right? Suppose A90 plan for getting the airport has 95% chance of succeeding. Does this mean it is a rational choice? So the A90 plan for getting to the airport, if it has 95% of chance of succeeding, does this mean it's a rational choice? So there may be A120 with higher probability of success. There may be A120 with higher probability of success. It may have a success rate of 98%, okay, but it may have more waiting time, right? There may be another plan, A1440, a plan that involves leaving home 24 hours in advance, right? This may have higher probability of success, so it may have 99% of success, but it will have more waiting time. Okay, so actually rationality depends on, like as we already stated, there are multiple goals. For each of the goals, how much importance you are going to give. So based on that only we'll define the rationality. So basically it will be decided by the programmer itself. based on the weightage or the importance of each of the goals. So there is a field called decision theory, which is a combination of probability theory and utility theory. So here utility means what are the performance measure you want to achieve. So the performance measures you want to achieve, that is called as utility plus probability. We combine both probability theory and utility theory. As a result, we get something, and that is called a decision theory. Okay. Right. Now let us have some brief look about probabilities. Like logical assertions, probabilistic assertions are about possible worlds. So in probability theory, the set of all possible world is called as sample space. So normally in AI we are calling as state space, whereas in the world of probability, the set of all possible worlds is called as sample space. Okay, and these possible worlds are mutually exclusive and exhaustive. What does it mean? So this is important. The set of all possible worlds are mutually exclusive and exhaustive. It means that there are many worlds, but out of these only one world can be true in a given time. Two possible worlds cannot both be the case. That is, two worlds cannot be true in a given time. In a given time, only one world can be true. That is called as mutually exclusive. That is, if one world is true, then all other worlds are false. And exhaustive means one world should be true at any point of time. One possible world must be the case. Okay. Mutually exclusive means only one world should be true and all other worlds should not be true. Exhaustive means in a given time, at least one in a given time, surely one world should be true. It is not that at one point of time nothing is true. No, at any point of time something should be true. That is called as exhaustive. Okay. Fine. So probabilities take the values between 0 and 1. So there are different cases that can occur, right, with probability. So when you sum up all those cases, basically you will end up with 1. So that is what this equation says. So probability of a event to get occur, that will take the value between 0 and 1. So like that, for different events there will be different probabilities. When you sum up all those things, you will get something as 1, right? The basic axioms of probability theory say that every possible world has a probability between 0 and 1, and that the total probability of the set of possible world is 1. Every possible world has a probability between 0 and 1. If you sum up the probability of all the worlds, what you will be getting is 1. Okay, right. So probabilities such as P of total equal to 11 and P of doubles are unconditional or prior probabilities. So here total equal to 11, in the sense, consider the case of rolling a die. So we are asking, like, what is the probability of total to have 11 when you roll 2 dice? Consider the case of rolling 2 dice. So what is the probability that the sum of the 2 dice values should be 11? Okay. And there is another question, like probability of having a double when you throw 2 dice. That is, in the first dice also I should get 1, second die also 1, or first die 2, second die also 2. That is, both the dice should have the same number. Both of them should have 2, both of them should have 3, or both of them should have 4, 5 or 6. What is the probability of that? So these are some of the examples for unconditional or prior probabilities. So there is no condition involved in this. We are directly saying that what's the probability of total equal to something, and what's the probability of this doubles. Okay. So this unconditional probability, basically they refer to degree of belief in propositions in the absence of any other information. They basically refer to degree of belief in propositions in the absence of any other information. Okay. Now, conditional or posterior probability of rolling doubles. Now the second thing what we are going to discuss is conditional or posterior probability. So this is the second case, conditional or posterior probability of rolling doubles, given that the first die is a 5. So, this is an example for conditional probability. So what is the conditional probability of rolling a double given that the first die is 5? Already you know that the value in the first die is 5. Given that, what is the probability that the second die also will be 5, so that it will lead into double? So this probability is written as P of doubles given that die 1 equal to 5. So here this is read as given that the probability of having a doubles given that die 1 is equal to 5. So this type of probability is called as conditional probability. It is one condition is already satisfied. Given this condition is true, what is the probability of the other to happen? Okay, right. So for any proposition phi, P of phi is equal to sigma omega belong to phi P of omega. So here this is an example of this total probability. For example, we want to say that the probability of total equal to 11. What is the probability of having total as 11 when you throw 2 die? So these are two cases. There are two cases, probability of 5, 6 and probability of 6, 5. These two things can lead into the value of 11. So probability of 5, 6 means first die is giving a value 5 and the second is giving 6. The first die is giving a value 6 and the second one is giving a value 5, right? So what is the probability of this? So that is the first probability of omega. Okay, so we can call it that as probability of omega 1. So that is probability of omega 1, that is nothing but probability of having 5, 6. Similarly, the probability of having 6, 5, that can be treated as omega 2. So the probability of having 6, 5 is omega 2. So the sum of these two things is nothing but probability of 5. Okay, so when you want to get the total of something, what are the different combinations of achieving this? So when you add up all these things, you'll get the total probability of that, right? So here is the formula for conditional probability. So conditional probabilities are defined in terms of unconditional probabilities. So probability of A given B is defined something like this, is equal to probability of A and B divided by probability of B. So this probability of B is an unconditional probability here. So probability of A and B, probability of A given B is equal to probability of A and B divided by probability of B. So this logic holds whenever probability of B is greater than 0. For example, probability of doubles given that die 1 equal to 5 is equal to probability of doubles and die 1 equal to 5. So what is the probability of having a double and die 1 is equal to 5? What is that probability? Divided by probability of die 1 equal to 5. So this is how we can calculate the conditional probability using unconditional probability, right? So there is also another formula for calculating the conditional probability. So here is another definition for conditional probability, which can be written as a product rule, right? Probability of A and B is equal to probability of A given B into probability of B. So basically it's the same rule. Basically this is the same rule. Only thing, we are taking this probability of B to the left. We are taking this probability of B here. Okay, so we are saying that probability of A and B is equal to probability of A given B into probability of B, right? So we'll continue this discussion in the next lecture also. For the time being, let us stop here. Thank you.